Welcome to the video on the Carnot cycle and entropy as a state function. Here we're going to try to show that entropy is in fact a state function. So, in order to show that entropy is a state function, we must show that the integral of some infinitesimal change in entropy ds is independent of the path. So, if the integral of our infinitesimal change in entropy ds around an arbitrary cycle is 0, then it must be independent of the path, because that guarantees that the entropy is the same at the initial and final states regardless of the path taken. So, if we look down here at some generic path, we have our initial state. As we go to our final state and then come back to the initial state, if the integral over that whole path from initial to final and back again, if that integral evaluates to 0, then entropy is a state function. So, what we need to show is that the closed integral, this symbol is wrong, it really should be a circle that looks like that. So the circle there represents a closed integral, saying that we're going from an initial state somewhere else and then coming back along some path. Doesn't matter what the path is, it's arbitrary. We need to be able to show that the integral of dq reversible, so this is the reversible heat, divided by the temperature of the surroundings is equal to 0. So, we're going to show this in 3 different steps. First, that the above equation is true, that that integral evaluates to 0. For a special cycle, we're going to use a Carnot cycle that looks something like this, involving an ideal gas. Then, we're going to extrapolate that result from an ideal gas for the Carnot cycle to a non-ideal gas using the Carnot cycle. And then, we're going to go from our special case Carnot cycle to any generic arbitrary cycle. All right, so let's look at the Carnot cycle. The Carnot cycle consists of 4 reversible changes. So we start out here at point A, and we have reversible isothermal expansion from A to B. So we're not changing the temperature as we go from A to B, it's isothermal, and we're expanding, the volume is increasing, so the pressure is dropping along this blue curve. And that's occurring at the temperature of the hot source, TH. So, then we have a mistake here. I'll go back and fix that. So, we have an equation that I don't have up there right now, and the second step, after we've had our isothermal expansion from A to B, is to have adiabatic expansion. So now we're not allowing heat to flow. We have adiabatic expansion along this adiabat, this reddish adiabat from B to C. So no energy is allowed to leave the system as heat. So the change in entropy must be 0, because if we go back, if Q is 0, because there's no heat transfer, then the entropy must be 0. So, the temperature is then falling, because we're not allowing any heat transfer. It's falling from the temperature of the hot source to the temperature of the cold sink. Alright, so we've gone from A to B, B to C. Now, we're going to go from C up to D. And so, here we have a reversible isothermal compression. So we're compressing, the volume is decreasing, and the pressure is increasing. It's isothermal, so it's occurring at the same temperature, which means that we have heat coming out of our system. And so the change in entropy of the system is delta S is equal to QC divided by TC. And so now this is QC is the heat going into our cold sink, and Tc is the temperature of the cold sink. And Qc there is negative because we have heat going out of our system. Heat leaving our system will be a negative heat, negative Q. All right, so the last step then is to move from point D back up to point A. So again, this is a reversible adiabatic compression. We're compressing the volume once more, only now we're not allowing any heat to flow out of our system, and so the pressure rises faster than it was along the isotherm. So no energy is entering or leaving the system, so the change in entropy must be 0 again, and the temperature increases from the temperature of the cold sink to the temperature of the hot source. So the total change in entropy around the cycle is the sum of the changes in each step. So here's the change in entropy from the first step, that equation that I was missing earlier. Then we have 0 from that second step, because it's an adiabatic change, so there's no heat transfer. Then we have our third step there. That's the isothermal compression. And then we have our fourth step. Again, it's adiabatic, so the heat transfer is again 0. And so, of course, if we take out the two zeros, then we're left with this equation. Okay, so in Atkins, in Chapter 3, Section 1, in Atkins Justification 3.1, he's able to show that this equation is true. And if that's true, then we can use this equation and this equation and substitute this into there. And we end up with this. So now we have negative Qc over Tc plus positive Qc over Tc. So that goes to 0. So remember, this is what we wanted to show. We wanted to be able to show that this integral was equal to 0. That entropy is a state function for a Carnot cycle involving an ideal gas. Right? So we've done this first step. Now we need to go from a Carnot cycle on an ideal gas to a Carnot cycle of a non-ideal gas. All right. Okay. So the way we're going to phrase this is, we need to show that the above steps apply to any material, not just an ideal gas. All right. So to do this, we're going to look at efficiency of a heat engine. So let's introduce the concept of efficiency. This symbol here is the Greek letter eta. Of a heat engine is defined as the work performed divided by the heat absorbed from a hot source. So with our heat engine, we have our hot source that's at some temperature TH. If we remove some heat, some QH, and here we're labeling this 20, so 20 units of heat, joules or whatever. Then we have some amount of that is going into a cold sink, that's QC. In this case, we've labeled that 15. And the cold sink is at a temperature TC. The remainder of that energy we get out as work. So, the work performed in this case is 5 joules or whatever, divided by the heat absorbed by the hot source, in this case 20. So the efficiency in this case would be 5 over 20. It's the absolute value of each of these, by the way. So 5 over 20 is 0.25. So we're only using a quarter of our energy to actually do work. 3/4 of the energy goes from the hot source into the cold sink. That's not a particularly efficient engine. Also note that because we have the absolute value here for work done and the absolute value for the heat, that makes the efficiency a positive value for all engines. All right, so we're able to change the work done, into heat and express our efficiency only in terms of heat, because the work done equals the heat transferred to the cold. The work done plus the heat transferred to the cold sink is equal to the total heat absorbed from the hot source. All of the heat coming out of the hot source has to go somewhere. That energy has to go somewhere. It either goes into the work done or it goes into the cold sink. So we can rearrange that like this. So the work done is equal to the total amount of energy that we took out of the hot source, minus the amount of energy that goes into the cold sink, that heat. That will give us the work, the absolute value there. And now, we can then replace the work that was on the top of this equation with these two. So we can plug that in. And then we can simplify this to get this equation. Okay, so we also can change from using the heat absorbed to using temperature. So if we can express the efficiency in terms of temperature, note that the absolute value signs are removing the negative. Now we get this formula. And now we have our efficiency is equal to 1 minus the temperature of the cold sink divided by the temperature of the hot source. So if we're looking at reversible engines, a reversible heat engine, it has the same efficiency as all other reversible heat engines, regardless of the construction, so regardless of what material it's made out of, whether it's an ideal gas or a non-ideal gas, as long as the temperature of the hot source and the cold sink are the same. So, the maximum efficiency is determined based on the temperature of the cold sink and the temperature of the hot source. The farther apart we get those two, so the higher the temperature of the hot source, the smaller this fraction becomes. And the lower the temperature of the cold sink, the smaller this fraction becomes. Right? Because if we want an engine that's really, really efficient, we want this fraction to be as small as possible. So we want the temperature of that cold sink to be really low, really close to absolute zero, and the temperature of the hot source to be really, really high. Alright, now, suppose we have a case like this, where we have not one heat engine, but two heat engines. So, we have one heat engine on the left here, that we're removing some heat from the hot source. Right. So again, we've shown that it doesn't matter what the construction materials of our heat engines are in the last couple of slides. So we have heat engine A is removing this heat, QH, from the hot reservoir, the hot source, and releasing QC to the cold reservoir. The difference between those two we get out as work, this W here. Now, suppose, for a moment, that engine A, is more efficient than engine B. And suppose we set engine B, to acquire more energy, to acquire energy as heat from the cold sink and push that up into the hot source. Now, as we explained earlier, it's going to take some energy to do this. So, we take some of the work that we're getting out of engine A and use that to drive engine B, and to drive this process of pushing heat from the cold sink up into the hot source. So, because engine A is more efficient than engine B, not all of the work that is produced by A has to go into pushing that quantity of heat back out of reservoir, out of the cold sink. We're setting this QC, the amount of heat that we're putting into the cold sink, is the same as the amount of heat that we're pulling out of the cold sink. Okay. So, because engine A is more efficient than engine B, the amount of work we get out of A is larger than the amount of work we have to put into B to move that heat back. So, if the heat added to the cold reservoir from A is equal to the heat removed from B, then the total energy of the cold sink is remaining constant, right? But let's look at the total energy of the hot source. Some work has been done. Right? If we're putting the same amount of energy back into the hot source, then we're violating the second law. We're still able to get some work out. But we can't do that. We can't violate the second law. So, our initial assumption that engine A is more efficient than engine B must be false. Therefore, the efficiencies must be independent of the materials or construction of the engines, and the heat's transferred, and the temperatures must also be independent of the construction and the materials of the engine. So it doesn't matter whether we have an ideal gas or a non-ideal gas. So, for any material, any kind of gas, involved in a Carnot cycle, the integral, and again we should have this symbol for the closed integral. The integral of our infinitesimally small changes in entropy must be 0. Alright, so we've shown the first step that the equation is true, that the integral evaluates to 0 for a special cycle, the Carnot cycle, involving an ideal gas. Now we've shown that it doesn't matter whether we have an ideal gas or a non-ideal gas, it's still true. Now we need to show that this is true for any cycle, that we don't have to have a nice Carnot cycle like this, we can use any arbitrary cycle we wish. Okay, so if we have some arbitrary cycle like this, we can approximate this as a collection of Carnot cycles like this. So we have some arbitrary cycle, that's this path here, although it could be any arbitrary cycle we wish. And then within that, we're going to layer on top of that a large collection of Carnot cycles, where we have our isotherms and we have our adiabats. Now, let's look at those cycles. So, the integral around the arbitrary path, that's this path that I'm drawing in red, the integral around that path is the sum of the integrals around each of these smaller Carnot cycles. So this is an approximation, but it's exact if the Carnot cycles are infinitesimally small, which we can do. We can just make them smaller and smaller and smaller. So, remember we've already shown that the entropy change around each of these individual Carnot cycles is 0. We've already proven that earlier. So, the entropy change around the entire cycle must be 0. Because again, the integral around the arbitrary path is a sum of the integrals around each of the Carnot cycles. So it's a sum of zeros. Alright. We can make some simplifying assumptions though. So, in the sum, the entropy change along any one path of the 4 that are in that Carnot cycle. So if we look at, say, this cycle here, we have 4 paths. As we're traveling down this path, as we go that way, that direction, that change in entropy is canceled by the corresponding, so this direction we are expanding the gas. It's canceled by the compression running that direction, along that same path. Those two changes in entropy, because they're on exactly the same line, those two changes cancel each other. So, that means that for each path along any of the interior regions, any of these interior lines, each of these paths is going to cancel with that same path, but in the opposite direction of the neighboring Carnot cycle. So, all of the entropy changes cancel except for those along the perimeter of the overall cycle. So, only those that are on this path. And so on. I won't trace them all. But only those that are on the outside are the ones that matter. So we have the sum over all of our Carnot cycles, over each individual change, whether it's an adiabat or an isotherm, is equal to, now we've shown that all of the interior sections don't matter. So we're just looking at the sum over the perimeter. That's still equal to 0. And now, in the limit of infinitesimally small cycles, then the perimeter, those portions of the Carnot cycles along the perimeter, match exactly the overall cycle, that arbitrary cycle. It matches it exactly, and the sum becomes an integral. So instead of having a sum, we now have an integral. Again, we should have a closed integral sign there. So now the integral of our reversible change in heat divided by the temperature of the surroundings for the perimeter is equal to the same integral over the arbitrary cycle for the same quantity, and that equals 0. So, now we've shown that the integral evaluates to 0 for any arbitrary cycle. So, if it evaluates to 0 for any arbitrary cycle, then ds is an exact differential, and S, entropy, must be a state function. So, entropy must be a state function. So that's the Carnot cycle, and entropy as a state function.